All right, good afternoon. Again, just picking up where we have been working with logarithms from the Test 4 Review Part 1. And now we have looking into, once again, working with expanding as well as combining logarithmic terms. And we have, in the case of going back to number 9, and here we have again, we have log. If you notice, we don't have a specified base, and anytime you have log, you're going to read this as a base 10 logarithm. And for what we have in the setup, okay, so if I rewrite what I have in the attachment, okay, so I have just taking what we have with the radicals, and if I express in terms of non-integer exponents, okay, so we have log, and we have the quantity, okay, and we have in the terms, okay, so I have 10 times u to the 3/4, and we have times x to the 5th. And for the cubic root of z to the 4th minus 13, okay, we can rewrite this as z to the 4th minus 13 raised to the 1/3 power. And for what we have in the denominator, okay, so I have the square of w plus 1 times y to the 2/3. And just looking at what we have here, okay, so just after rewriting, again, the radicals, or in this case, this radical, as a non-integer exponent. Okay, so again, we have log. Again, that is going to be a base 10 logarithm. And for what we have in terms of the expanding, okay, so just moving the items over here. Okay, so again, multiplication implies the operation of adding, whereas division implies the operating of subtracting. And for what we have in the statement, okay, so you have, so we got in the numerator, we have 4 factors with 10 u to the 3/4, x to the 5th, as well as z to the 4th minus 13 quantity to the 1/3 power. And again, we have 2 factors in the denominator. Okay, and so for what we're going to have here is that working with these terms, okay, so again, we have the log of 10, and you can put the factors in most any order. And what I'm going to do is I'm just going to take the top layer before working with the terms in the bottom. So I have the log of 10 plus the log in base 10 of u to the 3/4, and I have plus the base 10 logarithm, okay, of x to the 5th. And looking at what we have in following through, okay, so we have plus base 10 logarithm, okay, again, so you have z to the 4th minus 13 raised to the 1/3. Okay, so these 4 factors are at the top, and again, just writing in expanding notation, so I'm going to be adding these together. And with the square of w plus 1 and y to the 2/3 at the bottom, okay, the base 10 logarithmic terms formed with these as the attachments are going to be subtracted. So you have minus, again, so you have base 10 logarithm of the square of w plus 1. And again, we have minus base 10 logarithm of y to the 2/3. All right, and again, just kind of going back again, so with the property whereupon we have the base a logarithm of a to the x is equal to x, we have first situation to arise with the log of 10. Okay, so again, we have log of 10. Okay, so you're looking at a base 10 logarithm of 10. Okay, now you don't have the specified power, but this would be like if you had base 10 logarithm of 10 raised to the first power. And so that is going to be equal to 1. And for the other terms, okay, so we're going to have converting the exponents into coefficients. So for what we got now, okay, so we have the base 10 logarithm of 10 goes to 1. Okay, and so we have in the development, okay, so we got with the first term, okay, so you have 1, then we have plus 3/4 of the base 10 logarithm of u, and we have plus 5 times, okay, base 10 logarithm of x, and we have plus, okay, we have 1/3 of the base 10 logarithm, okay, and we have of the quantity of z to the 4th minus 13, and we have minus, okay, 2 times base 10 logarithm, okay, of w plus 1, and then finally we have minus 2/3 of the base 10 logarithm of y. Okay, and now for the attachments we have with z to the 4th minus 13 in parentheses, you just let those stay. You don't do anything like distributing, like having as separate logarithmic terms. And for what we have in the case of the exponent, like in the case of z to the 4th, that stays. You do not move this over to the front. That was already taken care of with the 1/3. Okay, so this will be the full expansion of what we have with this particular logarithmic term. And again, it doesn't have to be in this exact order. Just make sure that these 4 terms are positive, whereas the expressions we have with w and y are going to be the negatives. All right, now for what we have in the case of numbers 10 through 12, now we're looking at consolidating logarithmic terms into one logarithm. And for what we have in the case of number 10, okay, so you got 2 times, okay, the base 5 logarithm of 10 plus 3 times the base 5 logarithm of x, and we have minus 2 times the base 5 logarithm of y. Okay, so just some things we're going to have happening. Okay, so you have 2 times the base 5 logarithm of 10, okay, and okay, so when you're looking at consolidating, okay, if we have any coefficients in front of the logarithmic portion, okay, we're going to rewrite from converting from coefficient to exponent. Okay, so we have 3 is going to be the power to which x is going to be raised. And here we have for minus 2 times the base 5 logarithm of y. Okay, so that 2 is also going to be an exponent. Okay, so we have in following through, okay, so we have, in this case, right, so you have base 5 logarithm of 10 to the 2nd, and we have plus the base 5 logarithm of x to the 3rd, and we have minus, okay, the base 5 logarithm of y to the 2nd. Okay, now for what we have here, okay, we have 2 positive base 5 logarithmic terms and 1 that is negative, and just combining, okay, anything that is attached to positive logarithmic terms, okay, we'll have at the top anything that is attached to negative logarithmic terms, okay, you're going to have situated at the bottom. So you got 10 squared comes from a positive, so that is going to go to the top. So you got 10 squared. Likewise, we have x cubed. This will go to the top. And with y squared, this comes from a negative. So y squared goes on the bottom. Okay, and just sort of completing in one sense. And one could say this is a complete answer, but just taking care of 10 to the second. So we have a base 5 logarithm, okay, whereupon we have 100 x cubed all over y squared and so that is also another way that the final result can be expressed. Okay. All right, so we had the base 5 logarithm of 100x cubed all over y squared. Okay, now for what we have in the case of number 11, okay, so we have expressions in the variables u and v, and just looking at what we have here. Okay, so we had the leadoff term is 2 times, okay, the natural logarithm of u. Okay, so I can convert the 2 as an exponent, and we have plus 3 times, okay, the natural logarithm of v. And we have plus 1/2 the natural logarithm, okay, and we have of the sum of u and v, and this 1/2 again is going to be converted to a power, and finally we have minus 3/4 of the natural logarithm, and it's going to be of w to the 4th plus y to the 5th minus z. Whereby we're going to have 3/4 also as an exponent. Okay, so for what we have in the process, okay, so we've got 4 separate natural logarithmic terms, and I'm going to put these together and form a single natural logarithm. Okay, so you have the natural logarithm of u to the 2nd plus the natural logarithm of v to the 3rd, and we have plus the natural logarithm, okay, we have u plus v raised to the 1/2, and we have minus the natural logarithm of w to the 4th plus y to the 5th minus z raised to the 3/4 degree. And looking at forming a single term here. Okay, so you have the natural logarithm. Okay, so we have for the ratio that is going to be formed. Okay, notice you have the first 3 terms are positive, so all the attachments will go to the top. Okay, so you have u squared times v to the 3rd, and we have times the quantity of u plus v raised to the 1/2, and we have with the last term is a negative, okay, we have w to the 4th plus y to the 5th minus z to the 3/4 on the bottom. Okay, and there's another way that this could be expressed. Okay, so you have u squared, v to the 3rd, and again, alternate way of writing u plus v raised to the 1/2. Okay, if I expressed as a radical, okay, this will be the square root of u plus v, and again for this expression to the 3/4, again the type of radical is going to be indicated by the denominator of the non-integer exponent. So we're going to have a 4th root, and this will be of all of. w to the fourth plus y to the fifth minus z quantity raised to the third. Okay, so you got two different ways of saying the exact same thing. Okay, all right. Now, for what we have in the case of number 12, okay, now this is a little bit of a trick one because you had the simultaneous appearance of coefficients and radicals as well as exponents. And now for number 12, what I'm going to do here, okay, we have with the first term, I'll just go ahead and write these radicals in terms of non-integer exponents. Okay, so we got 12 times the base 5 logarithm, and for the cubic root of y minus 4, okay, so we're going to have y minus 4, and this is going to be to the 1/3. I can go ahead and move the 2, but I'll just do this at the next stage. Okay, and so for what we have here, so we got plus 2, okay, and we have times, okay, the base 5 logarithm of y squared plus 15, and we have minus 5 times the base 5 logarithm, and for the cubic root of y plus 5, I can write this as the quantity of y plus 5 raised to the 1/3 power. Okay, so just taking what we have here. Okay, so the only thing I've done right now is just write the radicals as non-integer exponents. Okay, so just kind of picking up from here. Okay, so we have, if you notice, okay, we have exponents, but we also have coefficients out at the front. Okay, and so what I'm going to do here, okay, is that we got the 12, the 2, and the 5. Okay, those are going to be performing along the lines of exponential operators. Okay, and so just looking at what we have here, okay, so for what we have, okay, so 12, okay, that's going to operate along the lines of exponential capacities. Okay, 2 is going to be a power, and 5, okay, that's going to have its own exponential capabilities. Now for what is going to arise here, so you have the base 5 logarithm, okay, and what's going to happen here, now you got y minus 4 to the 1/3, okay, and you have y minus 4 to the 1/3, okay, and this is going to be raised to the 12th power. So we're looking at the power property of exponents. And we have next in line, so you have plus the base 5 logarithm of the quantity of y squared plus 15 to the second and we have minus, okay, the base 5 logarithm, okay, and the 5 is going to affect the 1/3, okay, so you have, in this one case, you have minus the base 5 logarithm, and we have of the quantity of y plus 5 to the 1/3, and we have taken to the 5th power Okay, so you got a base 5 logarithm. Okay, so for y minus 4 to the 1/3 to the 12th. So again, if I have a base to a power, I'm going to multiply the powers together. And 1/3 of 12 is going to be 12/3, and 12/3 is reducible to 4. So I have the base 5 logarithm of y minus 4 to the 4th and again I have plus the base 5 logarithm of y squared plus 15 raised to the 2nd, and for the last term we have minus, okay, the base 5 logarithm. Okay, and for y plus 5 to the 1/3 to the 5th, again the powers are going to multiply, whereupon we're going to have in the attachment will be y plus 5 raised to the 5/3 power. And so looking at consolidating as a single base 5 logarithmic term, okay, so we're going to have here, okay, so we got, okay, with y minus 4 to the 4th, okay, this comes from a positive base 5 logarithmic term. So you have y minus 4 to the 4th. Next term is positive, so the attachment goes in the numerator. And for the last term, okay, this is positive, so this is going to go in the denominator. Y minus 4 to the 4th. Okay, you got 1/3. Think about here, to the side you got 1/3 times 12. You're going to multiply the powers together, and that's 12/3. And that reduces to 4. That's where that 4 came in. And again, just like what we had before, okay, we can write the non-integer powers as radicals. Okay, so again, so we have y minus 4 to the 4th, and we have times the quantity, and we have y squared plus 15 raised to the 2nd. And in the denominator, we have with y plus 5 raised to the 5/3. Okay, this will be the cubic root of y plus 5 raised to the 5th. And again, this is another way that the final answer can be displayed. All right. Now, going back to what we have with exponential equations, okay, where we had, first of all, okay, for those items that will share a common base, and we have n number 13. Okay, so we have in this one we have 8 to the x plus 6 is equal to 4 to the x. Okay, and so for what we have here, okay, now in terms of a common base, now 8 is a multiple of 4, but it is not an integer power of 4. And once again, we have with a common base, it'll be that number which will multiply itself into both 4 and 8. And again, that number is going to be at 2. So for 8 to the x plus 6, now 8 in terms of base 2, we have 2 to the 3rd. And for 8 to the x plus 6, again, for 8 to the x plus 6, we're going to have 2 cubed raised to the x plus 6. And for 4 to the x, okay, for 4 is going to be 2 squared. And we have 2 to the x. Okay, now for both of these situations now, we got the power property of exponents to deal with. Okay, so we got 2 cubed to the x plus 6, and what's going to happen here is you have 2 to the third, and that 3 is going to multiply all of x plus 6. And many will make the mistake of just attaching the entities together without fully distributing. In other words, like they can have like 2 to the 3x plus 6, and that is not accurate because you're looking at multiplying 6 by 3. So this left hand side will become, upon removal of parentheses, would be 2 to the 3x plus 18. Okay. And we have to the right, we got 2 squared to the x, so this will be 2 to the 2 times x. And now we have single base 2 terms, whereupon we have 2 to the 3x plus 18 is equal to 2 to the 2x. And if we got single terms and they both had the same exponential base, we can now set the powers equal to each other. So we have 3x plus 18 is equal to 2x. And we have in x, we have the lone, or the term by itself, to be at 2x. And I can join this with 3x upon taking 3x away from both sides. And so we're going to have the 18 is equal to negative x. And just changing the signs at both ends, so you have 18 is equal to negative x. So we're going to have that negative 18 is equal to x, and just formally declaring the solution. Okay, so the missing value for x, okay, that is going to be at minus 18. And for what we have in the case of number 15, okay, so we have an expression here, okay, whereupon we have 1 over 1,000 to the x is equal to 10 raised to the 1 plus x. Okay, so we have in 15. Okay, so you have 1 over 1,000 to the x is equal to 10 raised to the 1 plus x. Okay, now we have the common base already present. Okay, that number is going to be at 10. And looking at writing in terms of base 10, okay, now 1,000 is going to be 10 raised to the third power. So 1 over 1,000 is going to be 1 over 10 to the third. So 1 over 1,000 to the x is going to be 1 over 10 to the third raised to the x. And we have is equal to 10 raised to the 1 plus x. Now the right hand side is in base 10 in direct fashion. Now for the left hand side, I do have the base 10 present, but this is in reciprocal form. And just kind of a reminder, if you have like taking the inverse property, say if you have a base a to the negative x, that's going to be the same as the reciprocal of a to the positive x. And guess what? I have the reciprocal of 10 to the positive 3. And if I rewrite in terms of base 10 in direct terms, well, guess what? The reciprocal of 10 to the third is going to be 10 raised to the negative 3. And so we're going to have here for 10 to the negative 3 to the x, we have multiplying the powers together. So you have 10 to the negative 3x is equal to 10 raised to the 1 plus x. Okay, so we have, once again, we have single base 10 terms, and we can set the powers equal to each other. Okay, so I have negative 3x is equal to 1 plus x. And I got negative 3x by itself. And if I join this with x from the other side, so we have taking x away from both sides of the equation. So we have negative 3x minus x becomes negative 4x. And we have that negative 4x is equal to 1. And we have with division by negative 4. So we'll have here, okay, another negative fraction, whereupon we have x is equal to minus 1/4. Okay, and we'll get into the business application problems in just a moment. But just kind of as a reminder, okay, for the last case that we have concerning what we have for taking, again, common bases, as well as where we might have more than one term on either side of the equation. Now, let's say we have, in the case of say in solving for x, now let's say if I have something like 3 to the 2x, I'll say I have times 9 to the x minus 2 is equal to 27 to the 3x. Okay, and we have for this setup, okay, we already have the common base present, and that is going to be at 3. Okay, so we have for the first expression, okay, we have in terms of base 3, so you have 3 to the 2x. Now for 9 to the x minus 2, now in terms of base 3, 9 is going to be 3 to the second. And for 9 to the x minus 2, so we have 3 squared raised to the x minus 2 power. Now for 27, you also have it's both a multiple and an integer power of 3. And it takes 3 3's to multiply out to 27. So 27 is going to be 3 to the third. And thus 27 to the 3x is going to be 3 cubed to the 3x. And just taking what we have here for the base 3 terms. Okay, so we have 3 to the 2x. For 9 to the x minus 2, that's going to be, for right now, 3 to the 2 times all of x minus 2. And we have equal to 3 to the 3 times 3x. And so for what we have now, so you got 3 to the 2x. We had times 3 to the 2x minus 4. And that is equal to 3 raised to the 9x degree. Okay, so I have all of these terms now along the lines of base 3. Now I've got one base 3 term on the right, but I have 2 on the left. And what I want to do here is to make this into a single base 3 term. And this will be done by taking the base 3 and adding the exponents together. So we had the product property, which will, in this case, where we had the product property of the exponents, and we're adding the powers together. So we're now going to have 3 to the 2x plus 2x minus 4. So this is going to make 3 to the 4x minus 4. And we have is equal to 3 to the 9x. So I now have single base 3 terms. And I can now set the powers equal to each other. Okay. So I'm going to have 4x minus 4, is equal to 9x. Okay. And we have with this two-step linear equation, or what will be a two-step linear equation. Okay, so I can take 4x away from both sides. Okay, and I have now negative 4 equal to 5x. Now we have with division by 5. Okay, so we have negative 4/5 is equal to x. And just switching sides here. Okay, so we had the value of x to come out to minus 4/5. All right. Now, in looking at what we have concerning for number 25, okay, and we have with compound interest and future value. And we have here, it says to find the future value of $3,000 invested at 10%, okay, compounded. And we have, first of all, we have monthly after 6 years. And then we have B, we have continuously after 6 years. So you got the same amount, the same percentage rate, but in different contexts. And we had the same time span with 6 years. And we have, for the setup, in number 25, okay, so again we have P, the principal, or what is finance. Okay, we have $3,000. Rate of interest, okay, we have it 10%. And in recording the numbers in the calculation, okay, so the rate is going to be entered at 0.1. And for the time span, okay, we have for 6 years, and for A, so we have with non-continuous compounding, okay, we have this version of the future value formula. So we have A is equal to P times the quantity of 1 plus R over N to the N times T degree. And we have in the case of monthly compounding. Okay, so got the formula. Okay, and again, so for N is equal to 12. Okay, this is monthly. So just filling in what we have here. So we have P is going to be at $3,000. And for 1 plus R over N, so R we have at 0.1. And we have over N, again, which is going to be 12. And for the N times T, okay, N is at 12. T is at 6. So $3,000, okay, and for 0.10 over 12, and you're going to have repeating decimal with the number 3, and among the first digits, okay, we have 1.008, and then you're going to have repeating 3's to follow, okay, and for the exponent, okay, we have to the 72nd power. Okay, so here we have $3,000. And for this decimal, okay, so just let it carry on out and raise into the 72nd power. Now we'll have a number that's a little bit over 1.8. And among the first digits, we have 1.81759. And multiplying by $3,000. So we have here, okay, right at $5,452.78. Okay, so this is again for monthly compounding, and again for the same amount of money, same quoted percentage rate, and the same amount of time. Okay, the higher or the greater the frequency, the higher the balance is going to be. And given what we have here with the principal, the rates, and the time, Now the theoretical maximum is going to be whenever the frequency is going to be at its maximum. And in this case, this will be where we have continuous compounding, whereupon we're going to have a is equal to p times the value to which you're going to have in approaching infinity. So this portion here becomes the natural logarithmic base e raised to the r times t power. Okay, so we have p is at $3,000. And for e to the r times t, okay, so you have e to the 0.1, and t is going to be at 6. And here we have $3,000 times e to the 0.6. Again, e is at 2.718 number. And for e to the 0.6, okay, we have for this figure, this is also slightly over 1.8. And here we have right at 1.822. 118, and just carrying the decimal fully out and multiplying by $3,000. So the maximum attainable future value with the compound interest, okay, that is going to be right at $5,466.36. And so for this result, this will be about somewhere between $13 and $14 higher than what results with the monthly compounding. Okay, now for what we have with these formulas, okay, these are for one-time deposits. But let's say that if you have like multiple deposits, and let's say that someone is looking at a goal and they're kind of using like maybe CDs or a money market account, and they're looking at putting in a fixed amount at regular intervals, like whether it's monthly, quarterly, semi-annually, or even annually. Okay, and you have these repeated deposits, and the end goal might be to have enough money to buy a new car, or to buy a new kitchen appliance, or it could be just making a down payment to set up a mortgage. And this kind of financing, where you have the same kind of compounding of interest, okay, this is going to be what is referred to as an annuity. And there'll be two capacities, okay? And now the traditional annuity formula, this is going to be on the minimum side, okay? And let's say that for what we have here, okay, so for a fixed amount P, deposited n times a year. I'm going to do a little bit of color coding here. So you have for a fixed amount P deposited n times a year, let's see the way I can phrase this. So you have n times a year. At the end of each cycle, Okay, so you have the end of each cycle. And the cycle could be like month, semi-annual period, every 3 months. And we have into an account. Where interest is compounded again have n times a year. Okay, and you had the future value is going to be the following. Okay, so we have so again you have A, and the annuity formula is going to look like sort of an amalgamated version of the regular non-continuous future value compound interest formula, which it is going to be. Okay, so you still have letter P, and you have times the quantity. Okay, and we have in brackets, and inside the brackets you have the quantity, or in parentheses, of 1 plus r over n to the n times t minus 1 and we have times n over r. Okay, and now for what we have in this one, okay, so this is going to be the minimum side, and considering looking at things from a conservative estimate, okay, this is going to be a regular annuity formula. And let's say that for what we have, this is going to be at the end of each cycle. And now, and let's take as an example, if I'm looking at determining A, given the following. Okay, and we'll just say that we have with the quantities. Okay, so we'll say we have with the numbers. Okay, we'll say that we have, we'll just look at it from a monthly perspective. Okay, and we'll say we have $300 deposited at the end of each month. And we'll say we have for the rate of interest. Okay, we have the rate of interest, we'll say, is at 6%. So we have R is going to be at 0.06. And we'll say the time span we'll have for 5 years. And for N, okay, so N is going to be equal to 12. Again, so you had the frequency of the $300 deposits to be at the end of each month, every month, and you also have going hand in hand, you have the compounding of interest to be done monthly. Okay, and so we have putting in the information, the known quantities. Okay, so you have A is equal to P, so we have at $300 have times the quantity. Okay, so you have 1 plus R over N. So R we have at 0.06. And N is going to be at 12. And for N times T, so we're looking at 12 times a year for 5 years. We have minus 1. We have times N over R. Okay, so you have 12 over 0.06. Okay, so you have $300. Okay, so for what we have inside the brackets. Okay, so we have 1.005 to the 60th minus 1. Now for N over R, okay, so if I divide 12 by 0.06, okay, this will reduce to a whole number. And in this case, okay, we'll have 200. And for the lingering activity that's going on within the brackets. Okay, so for 1.005 to the 60th, okay, that number is going to be a little bit over 1.3. So you have among the first digits, you have 1.34885. Again, you have minus 1. And we have times 200. And we have with the numbers. Okay, so you have for the difference between 1.005 to the 60th and 1. Okay, so you have among the digits, and you'll just keep your full display from your calculator. So you have 0.3488501. Okay, and some digits that might follow. Okay, so taking this and multiplying by both $300 as well as 200, and it's going to turn out that for the future value, okay, so this is what we're going to have in the big picture. Okay, so you got $300 a month. Okay, and so for every year, okay, so you're looking at $3,600 a year. $3,600 a year for 5 years. Okay, this will be $18,000 for the lump sum of the deposits. And the rest of the balance will come from the compounding of interest, which is done monthly at a rate of 6%. And so we're going to have about like another $2,900 plus to be added. So we have altogether, okay, we have the future amount after 5 years. Okay, we got right at $20,931.01. Okay, and there's another part to this. Okay, so this is like the theoretically minimal side to it all. But let's say if you have just going at the other end of the spectrum, where you're looking at, let's say, just the maximum amount. And let's say that if we have, I'm just going to kind of repeat a lot of this. Without changing things too much. Okay, and let's say what I mean by other end of the spectrum. Let's say that you're looking at your theoretically maximum future value. And what's going to happen here, okay, say if we have for a fixed amount P, deposit N times a year at the start of each cycle into an account where interest is compounded N times a year, the future value is going to be. Now you're going to have the same annuity formula, at least that part is going to be like part of the process. It's kind of like a marker. And the difference between the maximum and minimum is just going to be one particular sum as the factor, and that is going to be 1 plus R over N. So it's going to be the traditional annuity formula, but for the theoretically maximum attainable balance. You're going to throw in the factor, namely the quantity of 1 plus R over N. Okay, so that's going to be the maximum that we have here. And let's say that just going back to our example. Okay, so you still have monthly deposits, time spans for 5 years, rate is at 6%, and adjusting. Okay, so instead of having the $300 put in at the end of each month, say you have like $300 deposited at the start of each month. Okay, and so for what's going to happen here is that we've got the same numbers, and this 20,931.01 is going to be used in configuring what the future value is going to be. And what I mean by this, with the start of each month, you had the slightest detail over this 1 plus R over N factor. And guess what? So you have 1 plus R, we have at 0.06. And again, N is going to be at 12. And so we have 1.005. And guess what? For this particular future value, so we have 1.005. And guess what? That's going to be times everything else with P, the bracketed statement, and N over R. And we had just determined that at 20,931.01. So that's going to be the difference between the maximum and the minimum. So taking 1.005 times this amount. Okay, and so for the future value in this case, this is going to be right around $21,035.67. Okay, so you have in the long run just like over $104 in the difference. Okay, and now where we have annuities concerned, and we have for number 26. Okay, so you have a bit of a compare and contrast. Now we have with Ray. Okay, now Ray is planning to retire, okay, in 15 years. Okay, and it says that he contributes $1,000 to an IRA on a semi-annual basis. So we're looking at twice a year. And it says that the rate of return is assumed to be 10% compounded semi-annually. And we have in part A, it's asking what would the minimum value of the IRA be whenever Ray retires. Okay, in other words, if he invested at the end of each 6-month cycle. Okay, so for what we have in the case of number 26 in part A. Okay, so again we have just sort of the backdrop. Okay, so you have again, so you had the principal, at 1,000, and the rate we have at 10%. And since we have semi-annually, okay, so N is going to be equal to 2 twice a year, or every half a year. And the time span we're going to have for 15 years. Okay, so you have A is equal to P times the quantity of 1 plus R over N taken to the N times T degree. So we have minus 1. We have times N over R. Okay. And so just looking at filling in the numbers. Okay, so yeah, P is at 1,000. And times the quantity. So filling in the numbers. Okay, so you have 1 plus 0.1. You have over 2. And again, for the exponent, so we have twice a year for 15 years. You have minus 1 and have times N over R. So you have times 2 over 0.1. Okay, so I have 1,000. Okay, so for the sum, okay, we have 1.05. This will be to the 30th. And minus 1. Now for 2 divided by 1/10, okay, that's going to come out to 20. And for 1.05 to the 30th, okay, now for this particular number, okay, this is a number that's going to be over 4. Okay, so we have right at 4.3219. And again, we're going to take away 1. You had the minus 1 in the formula. So you have $1,000. And you have times this difference, which you have right at 3.32194 times 20. And so the minimum in this case is going to be right at 66,438.85. Okay, so that's going to be the minimum of Ray's IRA, okay, after 15 years. Now for the theoretically maximum value, okay, so you got this number here, and here's you will see a bit of a gap between the amounts, much larger than what we had in just the examples with the monthly deposits of $300, like start of the month in comparison to the end of the month. With semi-annual deposits and compounding, so we have at the minimum, you can say that Ray has been investing like at the end of June and as close to the end of the year as possible. But at the other end of the spectrum, what Part B is looking at is where Ray is investing as close to the beginning of the year and as close to, let's say, like the 1st of July, as closely as possible. And the collective difference is going to be with the 1 plus R over N factor once again. So it's like adding a little layer, add a layer of 1 plus R over N. So yeah, again, so you had the rate of interest, again, was at 10%, and compounding was done semi-annually. So you got 0.05 added to 1, so you have a 5% difference. So on the maximum side, that 1 plus R over N times everything else, you're going to have 1.05 times 66,438.85 okay, and so we'll have a sizable difference here, and let me So in this case, we're going to have the A is equal to $69,760.79. Okay. All right. Now, and this could also be looked at upon, let's say, just how much you need to sock away every so often. Okay, say if you're looking at a future goal, and if you notice, say for number 27, okay, you're looking at an 18-year plan to arrive to $170,000 for a child's 4-year college education. And here we have a 5% rate of return, and the compounding is going to be done monthly. And so we're looking at how much must be contributed every month in order to have this particular amount in 18 years. And so we're looking at this future value formula, but now the 170 grand is going to be the future amount, and we're looking at solving for P, and we have in this particular case, right, so we're solving for P, and it says to round up to the next penny in your answer, not the nearest, but to the next. Okay, so we have okay, it's a backdrop here. Okay, so it is now A that is known. So A is equal to $170,000. And P we're trying to determine. And again, the rate of interest, again, that was at 5%. Again, the frequency of the compounding is monthly. So N is equal to 12. And again, we have for the time span, okay, that is for 18 years. And so in the case of 27, okay, so I have this formula once again. Okay, so $170,000. Okay, this is the end goal here. And again, we're looking at solving for P. And we have times the quantity. Okay, now we have 1 plus. And we have for R over N, so that's going to be 0.05 over 12. And for N times T, okay, so we're looking at 12 times 18 minus 1, and times N over R, so N is at 12, and R is at 0.05. Okay, so we have with the inside numbers here. Okay, so you have for 0.05 over 12. Okay, so you're going to have a repeating decimal, and for what is going to arise here, so we have 1.0041, and then you're going to have 6s to repeat, and for 12 times 18, so this is going to be 216, and we have minus 1, and 12 divided by 0.05, okay, that is going to be at 240. Okay, and for our decimal here, okay, that number, okay, we have right at 1.455. And still taking away 1, and again we have times 240. Okay, so got P. Now we have times. Let me back up. That should be a 2 point. There we go. So taking the difference. So that's going to be 1.455. Okay. So 1.455008. And just let the decimal numbers carry out, and multiplying by 240. So we have 170,000 is going to be equal to, and for the coefficient, and I don't like to write out all of these decimal places, but we're looking at bringing it down to pennies, so to speak. So you have 349.202 0215 times P, and if I divide 170 grand by this decimal amount, so you got P right at 486. And we got 0.82421. But again, I'm looking at rounding to the next penny. Okay, and so in this case, right, so to be sure that you're going to have, like, guaranteed at least $170,000, as opposed to like $169,999 and change. Okay, so you're looking at $486.83 per month. Okay, in order to arrive at $170,000 at the end of the 18-year goal. All right, and just quick items here. Okay. Now we had exponential equations with a common base. Okay, so looking at them with no common base, all right, we have just at the foundation. And what we're going to do here, you have just going back to your logarithmic properties. So you have a base A logarithm of a to the x is equal to x. And also you have your change of base formula, where you have the base A logarithm of m. Again, you have either the natural logarithm of m over the natural logarithm of a, or you can use the base 10 logarithms. Okay, and so just looking at what we have here. Okay. So you have the base 10 logarithm of m over that of a. Okay, so we got in this item, so you have the base 10 logarithm of m over the base 10 logarithm of a. Okay, now I'm going to take, just for examples here, okay, so if I have something like 4 to the x, I'm just going to take examples where you have just the variable on one side of the equation. Okay, there are going to be some problems with 2, but I'm just going to stick with 1 since we're kind of pressed for time. Now I've got 4 to the x is equal to 39. Okay, now think of it like this. 4 to the first is 4, 4 squared is 16, 4 cubed is 64. So 39 is between 16 and 64. So it's between 4 to the second and 4 to the third. So you can anticipate that x is going to be 2 point something. And using this property, I can get 4 to the x in terms of x. So I can take the base 4 logarithm of both sides here. Okay, so the left-hand side I have x equal to the base 4 logarithm of 39. And from this, okay, I can take the change of base formula. Okay, so you have the base 4 logarithm of 39. And I would use natural logarithm of 39 all over, okay, the natural logarithm of 4. And so we have say taken to about the nearest 4 decimal places. Okay, so you have x is going to be right at 2.6427. And if we have, let's say, large number here, and just kind of using this as the last example here, so you have like 100 to the x is equal to 15. And if I convert 100 to the x as just x, so I'm taking a base 100 logarithm of both sides here. So left hand side becomes x and for x, okay, so if I use the change of base formula, okay, where m is at 15 and a is at 100, and I would just go with the base 10 logarithm ratio on this one. So I had the base 10 logarithm of 15 over that of 100. And so for your value x in this case, so it's going to be about 100 raised to the point, let's say about 0.588 is going to be equal to 15. Okay. So we have for x, we have right at 0.588.